Okay, so if you didn't notice, I am not Gabe Robins. My name is Nathan Brunel. I'm one of Gabe Robins' grad students. And what this means is since Gabe Robins is here, there's no professors, so there's no rules, so we get to party today. So pay attention, I've got a prop up here, we're going to get to this later, but be considering exactly what's going on with this drinking bird. So where exactly is Gabe Robins? Well, he could be off shooting down helicopters or whatever. So if you didn't know, Gabe Robins is actually a meme. This is a meme that was really, really popular in Europe a few years ago. I haven't seen it around here lately, but being the nerdy guy shooting I think that's a Stinger missile launcher. Correct me if I'm wrong. That's just the kind of guy he is. He could also be underwater somewhere, I don't know. He could be roller skating in Southern California in like the 80s. Or he could be hanging out with some of his buds. Who knows? I have no idea where he is. That's a lie, I do know, but I'm not going to tell you because it's more fun this way. So starting next week, I'm still working on a location, but on Monday nights we're going to have these problem-solving sessions, which are going to include free pizza. So all that's going to happen is you're going to show up to these things. Many of the TAs are going to be there. I'm going to be there. And it's just a time for you to show up, meet your classmates, form study groups, work on problems, and you'll have almost immediate access to several TAs to help you solve these problems. So I'm pretty sure Professor Robins made it clear last week that the ultimate strategy for this course is really very clear. Just show up to lecture, do your readings, and solve lots of problems. So if you do those three things, then I can virtually guarantee that you're going to get an A in the class. So I like to tell people all you have to do to get an A in Theory of Computation is eat pizza. So that's almost true. So today I'm going to start out a little bit by talking about why exactly we study theory. Who has any opinions? Why is the study of theory in general important in any field, regardless of its computer science or engineering or physics or anything? Why do people study theory? Yeah. Yeah, so theory can give you kind of a framework for what things can and cannot be done, so you don't spend a lot of time doing something that you only find out is impossible later. What else? Who doesn't want to take this class? Just real quick. Yeah, so we're in an interesting spot in computer science because this is an engineering field, which is like a very practical field. As most people would consider it. So you're here looking to get a job as like a software architect or something like that, making the next multi-billion-dollar web page. And it's kind of hard to see where this fits into it. So I'm hoping to convince you that, or we are hoping to convince you that studying theory is interesting and important for one reason or another. And to convince you of this, I'm going to start by talking about an older example of theory that precedes computer science. Who knows what this is? Any guesses? Yeah, this is a heat engine. I heard it from up front. So this is specifically a model of a steam engine. So we have this fluid in here, which in a steam engine, that would be water. And here you have some sort of boiler or furnace or something where you've got a fire that's going to heat up the water. The water is going to expand and travel up because you've got this one-way valve here. It's going to travel up, and this movement will spin some turbine, which will produce some work. Maybe it'll move your train forward. It'll go down to this cooling unit, which will hopefully recondense this steam that was formed up here into water. And then it will, after being cooled, the water will move back into the furnace and repeat. And you cycle over and over and over again so that as long as this is hot and that's cold, this engine will keep running indefinitely. So back when steam engines were kind of this new hot thing, that pun was not intended. people were trying to figure out how could we get more efficiency out of the steam engine? What if we burned oil instead of coal? Or what if we used something other than water inside the steam engine? So there were all these questions of, all right, how can we get the most efficiency out of our steam engines? Can we make it more efficient by adding alcohol to here instead of water? So then along came this guy, Nicolas Carnot. So he was a physicist, and you can see here the 19th century, early 19th century. And he came up with this model here, which is called a Carnot engine, where it just simplified down, it just distilled down to the most simplest components what exactly a heat engine does. Where you've got some heat source, and you have some heat sink. So you've got a hot part of the engine and a cold part of the engine. And you have heat transferring from the hot part to the cold part. And while that happens, some work is produced. And through this super simplified model of an engine, he was able to prove that the maximum amount of work that a heat engine could do was dependent only on the temperature differential of the hot part and the cold part. So it doesn't matter if you replace the water with alcohol, or you used oil instead of coal, or anything like that. All that mattered was how hot this was compared to how cold this was. You could only get your engine more efficient by either making that hotter or that colder. If you didn't do that, then you weren't going to make it more efficient above a certain amount. Let's see here. I forgot to do these. Okay. So an interesting point here is that this model of a heat engine actually motivated the second law of thermodynamics. Anybody know what that is? The second law of thermodynamics? Shoot, because I forgot it. Yeah, go ahead. I think that's the first law. Is that the second one? What do I know? I forgot. Somebody look it up and tell me. You all have laptops. So we want to do something similar in this course with computation. So Carnot took engines, simplified them down to these very simple pieces that were easy to reason about and prove things about. We want to do the same thing, but with computers. So we need a simple set of ideas about what computers do in order to formalize them very precisely. So what is it that a computer does? Who can name some things that a computer does? Yes? It does what you tell it to do? Okay. Will it do anything that you tell it to do? If I told this computer right now, like, go do my laundry, is it going to do my laundry? Okay. Yeah. It does math? Okay. Does it do all math? Right, so that's one of the things we're going to study in this course, is computers actually don't do all math. That's one of the major results of the theory of computation, is we can prove that there is some math that a computer can't do. Yes? Okay, so it takes input. What's it do with that input? Yeah, so it takes some input and produces some output, is kind of the simplest thing we can think of a computer doing. So it implements some function. That's still a little bit high level for what we'd hope to do, but yeah, go ahead. Okay, so from a finite set of rules, it reads and writes symbols. Okay, that's good. That's a really good model. So this is what I say a computer does. You have some sort of computing machine or program, say your computer, and it'll take an input, and it either accepts or rejects that input. So what kind of problem is this? So this is computing a function, as was mentioned before, where it takes some input and gives an output. But specifically in this case, the output is accept or reject, or true or false, or 1 or 0, or something like that. What do we call that kind of function? Yeah? Okay, yeah, it's a binary function. There's a particular word in computer science. If you've taken algorithms, you've probably heard it before. If not, I'm not sure. But there's a specific type of problem that we call this. Yeah. A Boolean problem, okay. What else? You were going to say that? Okay. Any others? Yeah, all the way in the back. Yeah, that's the answer I was looking for. This is called a decision problem, where it just looks at this input and it makes a decision, do I accept it or do I reject it? So we're going to, for most of this class, restrict ourselves only to decision problems. That is, our program will take some input and it will answer either yes or no. Typically, we call those accept or reject in this class. So that's kind of the simplest kind of problem that we could think of. If anybody needs a chair, by the way, second row here, there's one more chair. Any questions so far? Does this make sense? Okay, so now what we need to do is consider what could go in this black box. So there's a lot of options for what we could put in this black box. So you could say, all right, well, we want to put a MacBook in that black box. Or maybe a big supercomputer. Anybody know what supercomputer this one is? I believe this is Stampede, which is in Texas. Look that one up. It's a really interesting supercomputer. Professor Robins is actually going to show you later on in the course that Tinker Toys could actually fully simulate any computer that you want. So you could build computers out of Tinker Toys. Or planetary systems. So if these are orbiting planets, you can actually simulate computers using orbiting planets if you could get them in the right positions with the right relative velocities and masses and all of that. He'll talk about that later. Or the ultimate computer, as far as we know right now, which is humans. So like all of these things are things that we could put in that black box. But all of them are a little bit complicated to just sit down and reason about in the way that we would reason about Carnot engines. We want to have some simple set of rules that we could use to prove things about computers. And if we're using like a human being or a laptop, it's kind of hard to prove things about those. By the way, this guy, his name is Wim Klein. He was called CERN's first supercomputer. His job title was actually computer. So computers used to be human beings. So the machine that you have in front of you assumed that title of computer from humans. So that was kind of the original computers stealing jobs from humans. The first job a computer stole from humans was a computer. So he was hired by CERN in 1958 after spending about 2 decades as a circus performer doing mathematical tricks, basically. And eventually he was replaced by a machine. He was replaced by a computer in 1976. This guy, he was really impressive. So the CERN physicists would like give him equations with like values, and his job was to evaluate those equations with those values and give the result back to the physicists because they couldn't be bothered with complicated arithmetic, I guess. But on the day he retired, he had this big performance in front of CERN. So you see on the chalkboard behind him, he's taking the 73rd root of this number, which is 500 digits long. He did that in 2 minutes and 43 seconds completely in his head. And eventually he was replaced by a machine. It's kind of like whose jobs are safe at this point. So anyway, off of that aside, back to this. So what could go in here? Somebody before mentioned a good, very simple set of rules for what a computer could do, which was that you? Say that again. Yeah, so a good idea for what might go in here is that we've got some sort of finite set of rules to define a procedure, and then it acts on that procedure. That's still a little bit vague, but that basically describes what a program does. So really in this class, what we're talking about is what we could put in this black box. So if we look at this, what we're going to look at in this class is a lot of formal languages. So we're going to look at these black boxes, which implement a decision problem. Each of them implements a decision problem. We're going to talk about something called a language, where a language is the set of all input strings which are accepted by this machine. So every symbol, every possible string that we could give you, and I haven't defined string yet, but this is exactly the same as what you would expect, like the string class in Java or something like that looked like. It was just a list of symbols. So for each input string that we could give, we're going to put it into this machine, and it's going to either accept or reject every one of them. And now we can consider something called a language, which is exactly the set of all of the strings which that machine happens to accept. So you can kind of think about this as a dictionary, where it's a set of words, and any word that this machine answers accept to is going to be considered as part of that dictionary. And the core idea of this class is that we can look at the different powers and limitations that we can assign to the machines which satisfy this black box, and compare those to what characteristics of languages are possible for that type of machine. So for instance, we could consider that it's a machine that is your MacBook. So your MacBook is one potential thing that could go in there. The question is, what languages can or cannot be computed by your MacBook? This is similar to saying what functions can you versus can't you compute with your MacBook. But like I said, we want something simpler than a MacBook. So we're going to be iterating through several different possibilities of what we could fill into this box and comparing those languages, those functions that they could compute. Any questions so far? So again, the whole overall idea of the course is how machine powers, different powers you let the machine have, change which languages or which functions are computable by those machines. And the first thing we're going to look at, and we'll get to this today if we have time, otherwise we'll get to it on Thursday, is something called regularity. So there's some category of languages, we call them classes of languages, which are called regular languages. And we get these languages when we have a model of machines, of computers, where the amount of memory that that computer has is extremely limited, or even if the computer has no memory at all. So that is, you can think of this as what happens if the type of machines we have in here, or the types of programs we have in here, are programs where you're not allowed to have any variables, for instance. So if you can't have any variables that you read from memory or wrote to memory in your computer, what functions can you compute versus can't you compute? So that's what regularity hints at there. And once we have the right set of rules, we can talk about this in a very precise way and convincingly prove things about those types of programs. And you'll see how, hopefully Thursday. Any questions? All right, so now we're going to talk a little bit about languages. So I mentioned at a high level what they were. We're going to more formally describe them right now. And so the word languages, the reason we use that is because the techniques that we use to talk about languages were actually borrowed from linguistics. So Noam Chomsky, who's heard of Noam Chomsky? Yeah, so he's kind of a really big political philosopher now. He started his career as a really influential linguist. But a lot of his ideas are actually highly relevant in theory of computation and computer science. And you can see some of that by the fact that these are called languages, that we talk about languages. But really, a language is just a set of strings. And what is a string? In order to find a string, we need to talk about an alphabet. So an alphabet is a finite set of symbols. That's all that it is. So we've got some set of symbols. It has to be finite. We call that an alphabet. So here's some examples. So typically we use this capital letter sigma as the variable for an alphabet. And we just say, all right, well, sigma, this alphabet, is going to be some finite set of symbols. So if it's the binary alphabet, those symbols could be just 0 and 1. This is the alphabet that your MacBooks will use, that your computers will use. It's just 0 and 1 is the whole alphabet. Another thing we could consider is maybe 0 through 9, where this is the decimal alphabet. So the arithmetic that you typically do by hand in elementary school is just over the decimal alphabet. We have a symbol for each of the numbers 0 through 9. You could also consider like the English alphabet, or here I call this the Sesame Street alphabet. So this is A through Z. So all of these are different valid alphabets. And whenever we're talking about a language, we're going to talk about it over some fixed alphabet. And for most of the times in this class, we're going to consider only very small alphabets. So it'll be 0 or 1, or just A and B, or A, B, C, and D. You'll only very, very rarely see an alphabet of size greater than 4 in this class. Why is that? Anybody have a guess as to why we're only going to consider alphabets of size 4? Or small alphabets? Yeah. Yeah, so if we talk about like strings over each of these alphabets, the bigger the alphabet is, the more strings you have for a certain length. What advantage might a larger alphabet give us over a smaller alphabet? Yeah. Right? Why is it that your computer could use only two characters in your alphabet? Yeah. Okay, so it's convenient for a computer to use that because you can say if the voltage is high, then it's a 1. If the voltage is low, then it's a 0, and you've got some threshold in the middle. We could make, instead of binary computers, we could make ternary computers. In fact, those have been made in the past, where you have 2 thresholds. So if it's above the upper threshold, then it's a 2. If it's between the 2 thresholds, then it's a 1. And if it's low, then it's a 0. Why don't we do that? Yeah. Okay, measuring the thresholds takes time. Why else? Yeah. Yeah, so you have increased error because these 2 thresholds, they have to be closer together, right? And there's always a little bit of noise with your computer through cosmic rays hitting it or fatigue of the hardware over time or whatever. And you could get error in reading one symbol versus another symbol. Why else? Yeah. Exactly. How? Okay. So what do we do if let's say I wanted to type in the Sesame Street alphabet on the computer, right? That's a thing that you do all the time. Many of you are probably doing it right now. That you type on your keyboard, and when you type on your keyboard, the letter A pops up onto the screen. How did the letter A pop up on the screen if your computer only had 0 and 1? Yes. Yeah, each letter can be represented by a string from a shorter alphabet. So you have ASCII encoding of your characters in your computer, where you have a string of 1s and 0s, each of which encodes a symbol from a larger alphabet. So actually, 2 characters are sufficient in order to represent any other alphabet that you might want. So because 2 is sufficient, if we can talk about what computers can and cannot do over alphabets of size 2, we've also talked about what they can do on alphabets of size 3 and size 4 and size 5 and so on. because anything from any larger language could be encoded using only an alphabet of size 2. How many understand that? So by considering we only need to consider smaller languages, because if we wanted to do a larger one, we could just encode that larger one using a smaller one, and any results we had here are going to apply to the case of the larger alphabet. Question? Yes? The short answer is you'll see. There are going to be some cases where if you only have one symbol in your alphabet, it can mess some things up. So if I have like characters followed by characters followed by characters, and I want to encode that using only a one symbol alphabet, then it's hard for me to tell when one character starts and the next one begins. So for instance, if I wanted to encode an A using five ones and a B using 7 ones, for instance, how do I know when I have 7 Bs versus 5 As? Because both of them are going to have 35 ones in a row. So there's some issues with that. That's a very good question, though. So there are some cases where you can use just an alphabet of size 1, but not in every case. 2 is kind of the minimum that is going to be like ultimately useful. Any more questions? Okay, so from an alphabet, we can talk about strings. So if an alphabet is just some finite set of symbols, a string is a finite sequence of those symbols. So for instance, if our alphabet was just A and B, these are some strings we could have. We could have just the string A. We could have AB. We could have AAA, BA, BBA, and so on. So any of these are valid strings. So any finite sequence, emphasis on the finite here, we're only going to be talking about finite length strings in this class. So any finite sequence of symbols is going to give us some string. And here, since we have a sequence, order matters. So like the string AB is different from the string BA. How many understand this? And this should be exactly what you think of when you think of like a string in your Java program or your Python program or something. These are the same thing. Here's some examples over the Sesame Street alphabet. And notice this isn't anything comprehensible in English, but it's still a string. Any questions on strings? Okay. We can talk about some operations we can do on strings then. So if a string is just a finite sequence of symbols, then we can talk about the length of that string. And the length of the string is kind of the obvious thing, just the number of symbols that are in that string. So exactly what your Java program does when you call string.length. So Nathan, the length of string Nathan is 6, and this is notation for the length of a string. Same as the notation for set cardinality. We can also concatenate strings. And there's 2 different notations we use for concatenating strings. So here we've got string W1 and W2. We can concatenate them by just listing them right up next to each other. Or we can use this dot notation. So W1 dot W2 also means concatenation. And it just does exactly the thing you expect. If I take the string AAAA and I concatenate it with the string BBBB, then you just have the first string immediately followed by the second string, now as a single string. So we have 4 A's followed by 4 B's. Now notice that the length of W1 concatenated with W2, so the length of this resulting string we get by concatenating the two, is the sum of the lengths of the original 2 strings. Does this make sense? Got me so far? Questions so far? So now that we have concatenation, we can talk about string exponentiation. So when we talk about the exponentiation of strings, we talk about iterative concatenation. So when we talk about exponentiation of like numbers, that's iterative multiplication, right? So when we have 2 to the third power, it says 2 multiplied by itself 3 times. When we have exponentiation of strings, so if we have some string w to the exponent of k, where k is some number, then that is that string concatenated with itself k times. So for instance, if we have the string that's just the single character a, and we concatenate it with itself 5 times, we get 5a's. So a exponentiated 5 is 5a's. Or if we have the string ab raised to the third power, ab, ab, ab. And the length of some string w raised to the k power is just the length of that string times k. Yes? That's a very good question. So we have some special string called the empty string. So this is like the double quotes that you had in Java, if you have open quote, close quote, or something like that. So this is the string that has no characters in it. And in the case that you have some string raised to the 0th power, you get this empty string. So the empty string, usually the way that I'll write it is using this lowercase epsilon here. But you'll see it on occasion in the problem sets as this caret symbol, so don't be thrown off by that. That means empty string. And this has some special properties to it. If we have any string w at all, and we concatenate w with the empty string, we get w right back. Does that make sense? Any questions here? Okay. The length of the empty string is 0, so it has no characters in it. And for any exponent we put to this epsilon, to this empty string, we get the empty string right back. Who can prove this real quick for me? Anybody want to do a quick proof of that? Yeah, you want to try? Okay. Yeah, so the empty string is unique, right? Because any string of length 0 has to contain no characters, which we said by definition was the empty string. So what you can do is you can just say, all right, well, if we have the empty string and we concatenate it with any string by this first term here, then we get that first string back. So if we had, say, e to the k, or this empty string to the k power, we could take out one of the e's and say the empty string concatenated with k minus 1. Right? So empty string concatenated with empty string to the power k minus 1 has to be equal to empty string to the power k. But we have that w concatenated with the empty string is equal to w no matter what w is. So that means that the empty string to the power k has to be equal to the empty string to the power k minus 1. And you can either by induction show that that means that you have to have the empty string, or there are other ways that you can do it without induction. But hopefully it's obvious from there that the end result has to be the empty string here. Any questions? Okay, so now we've talked about alphabets, which are a finite set of symbols, and strings, which is a finite sequence of symbols. And from these, we can talk about languages now, which a language is a set of strings. What word is in both of the above definitions that's not in this definition? Finite, exactly. So a language can be infinite. It may be infinite. It could be finite, but there could also be cases where the number of strings in a language is an infinite number. So here's some example languages. So this is a language over the binary alphabet. And it's specifically all of the strings of length 2 over that binary alphabet. This is the language of all the names that you can call me. And now we have some special language here that's called the empty language. So you can use this null symbol or open close brackets. So this is the language which contains no strings. This is different from this language. Be very careful of this. This is a common mistake. So this empty language is different from the language containing the empty string. This has no strings in it. This has one string in it, but that string just happens to have no characters. Who understands this distinction? Any questions so far? What is the size of this language? Shout it out. 0. What's the size of this language? 1. Very good. And now we can talk about some different operations that we can do to languages. So we can talk about language concatenation. So we have the same notation as before. So when we say we have language 1 concatenated with language 2, the definition, this is here, this is complicated. Hopefully by the end of the semester you'll get good at reading these. But what this says is we're going to take some string from language 1, so W1, which came from language 1, and we're going to take W2 from language 2 and concatenate them together. And all different ways that we can do this combine to produce the language, which is the concatenation of language 1, language 2. So it says take something, all the ways you could take a string from language 1 and concatenate it with a string from language 2. So here's some examples. So if we have the strings Linus, Charlie, and Sally, and we concatenate that with the language of Brown and Van Pelt, then we get Linus Brown, Charlie Brown, Sally Brown, Linus Van Pelt, Charlie Van Pelt, Sally Van Pelt, etc. So we took all of the strings in the first language and concatenated it with each of the strings in the second language to produce this third language, which was the concatenation of these two. Does this make sense? Any questions so far? So this behaves similarly to a cross product. Yeah.
Is this like well-defined for a language, and is it like
I'm not following.
so you got like everyone else too?
Mm-hmm. So the question is, what if L2 happened to be a subset of L1? Would the concatenation of these two languages just be L1? Does anybody want to try to answer that? Let's see if this fancy pen thing works real quick. No, it does not. Okay. Yeah, I saw a hand. Yeah, if L1 contains all of L2, so every string that is in L2 is also in L1, does it still make sense to talk about the concatenation of L1 with L2? Yeah. Exactly, yeah. So if this was Linus, Charlie, Sally, and this was just Linus, for instance, then we get Linus, Linus, Charlie, Linus, Sally, Linus. And that would be our language. Does this make sense? Yeah. Correct. Order matters here. So order matters with concatenation. Very good question. So this behaves very, very similarly to a cross product of sets. So who remembers from like discrete math what a cross product does? Who wants to say what a cross product does? Any brave souls? Yeah, go ahead. Yeah, all the different ordered pairs you can create from the two different sets. So if I have set S1 and I concatenate that with set S2, then it's always I can take an item from set 1 paired with an item from set 2. So it's all possible ways of doing that. So if I had a cross product of set 1 versus set 2, what would be the size of the set S1 cross product S2? So S1 cross product S2, this gives us some new set. What's the size of that set? Yeah. Yeah, take the size of set 1 and multiply it by the size of set 2. What about here? If I have a language 1 concatenated with language 2, what's the size of this language, of this new resulting language? So notice this down here is still a language, right? Because each of these are strings. This is a set of strings, so it's a language. So what's the size of L1 concatenated with L2? Yeah. It is at most the product of the cardinalities. So I was trying to trick you there. So L1 concatenated with L2 is going to be less than or equal to the product of their cardinalities, of their sizes. Here's an example for when it's less than. So if I have A and AA concatenated with itself, there's only 3 strings in this resulting language, whereas there were 2 in each of these. So if it was exactly the product, I should have 4 languages here. Why are there only 3 languages here instead of 4? Or 3 strings here instead of 4. Yeah. Exactly. There were 2 ways that I could produce AAA. I could do A with AA or AA with A. Right? So these were 2 distinct elements in the cross product of these 2 languages, but they happen to be the same in the concatenation. How many understand this? Okay. Questions so far? Yeah. Sorry? So all the notations on the board? So the L1 concatenate L2. There's 2 ways we can denote concatenation. One way is just push them together. Push the 2 language symbols together. That indicates concatenation. Or you can put this dot between them, similar to multiplication. You might see other ways in the wild, but these are going to be the only 2 ways I'll use them. And then this is set builder notation. Did you guys discuss set builder notation at all in like discrete math or something like that? So you're familiar with most of these. But this says the set of W1 concatenated W2 where such that W1 came from L1 and W2 came from L2. So all concatenations of pairs of strings where the first one was an element of language 1 and the second string was an element of language 2. Does this make sense? Okay. Any more questions? Yeah, this is going to be super important for you to like internalize and be able to just work with intuitively, because this is going to show up like all over the place all the time in all of your problems. All right, so now we can talk about language exponentiation. And this is the exact same idea as what we did with string exponentiation. So we can say that some language to the k power is that language concatenated with itself k times. So this is exactly the extension from strings to languages that we had with concatenation, but now we have it with exponentiation. So we can define it as L to the power k is L concatenated with L to the k minus 1. What happens if we have L to the 0 power? Who can guess? Yeah. Yeah, so in this case, you're actually going to get the language containing the empty string. It's not the empty language in this case. So similar to like any number n to the power 0 is 1. Any language to the power 0 is the language containing the empty string. So here's an example. So if we have Alan, the language of Alan and Mary to the power 4, then it's all different ways of concatenating 4 things from here. And order matters. So we have Alan, 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 or Alan, 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 Mary, or Mary, Alan, 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 Mary, 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 Mary. So any way we can take 4 things from here and concatenate them together over and over again. Who understands this? Okay. And here we go. And now similarly to before, if we have some language L to the power k, the length of that is going to be less than or equal to the length of L to the power k. So the size of that the size of the language exponentiated k is going to be less than or equal to the size of that language to the k power. Questions? Okay. And we also get all of the set operations with languages. So anything that you could talk about doing to a set, you could also talk about doing to languages, because languages are sets. So we can union together languages. If we have language 1 union with language 2, that's the set of all strings, W, such that W came from language 1 or W came from language 2. And we can, you'll sometimes see either of these notations for union, either the plus sign here or this cup sign. So for instance, if we had the language George and Paul, and we union that with Ringo and John, then we get George, Paul, Ringo, and John. Questions? Yeah. Yes, so sets by definition contain no multiplicity. So you can't have the same string in the same set twice. So when you union together these sets, it'll remove multiplicity. Good question. More questions? So here's a new one. So this is called Kleene closure. There's a few different ways that people try to pronounce this word. According to Jack Davidson, who claims that he heard the pronunciation from the son of the namesake, this is pronounced Kleene. Oftentimes you'll hear it clean or Kleene. I won't correct you because I haven't heard it from the horse's mouth what the correct pronunciation should be, but just be prepared for any of those. So this is, the notation for this is this star in the exponent. So L star, that's the Kleene closure of the language L. And intuitively, this represents 0 or more copies of strings from that language all concatenated together. So specifically, it's L to the 0 power, union with L to the 1 power, which is L itself, union L squared, union L cubed, and so on, for all different exponents we could do. So for instance, if we looked at the language with just the character A, and we did the Kleene closure of that, then we would have A to the 0 power, which is the empty string, A to the 1 power, which is just A itself, A to the 2, which is 2 A's, 3 A's, 4 A's, 5 A's, and so on. I think my slides got a little bit out of order here. So, where'd it go? Okay. So I'm gonna add some more examples in here as we go. So really, if I wanted to be more formal, this would be like that. So the language A raised to the star, that's the same thing as the above there. I could also do AB raised to the star. So just shout out some things that are in this language. Okay, so empty is one of them. A, that's another one. What else? B, okay, what else? AA. BB. AB, okay, what else? BA, very good. What else? Sure, 3 A's. I could have ABA, BA, BA. I could have BB, 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 and so on. How many things are in this language? Yeah. Yeah, so if the language L contains, so as long as the language L is not either the empty language or the language containing the empty string, then that language will always have, L star will always have an infinite number of strings in it. Why? Because I'll have at least one string of length 0, and at least one string, or at least, let's start over. So the reason for that is because I'll have at least one string from L0. In every case, that's going to be the empty string. I'll have a string that's just one copy of the thing from L, which will have more than 0 symbols in it. I'll have a string that is 2 copies from L, which will have more than some string here. I'll have a string formed from 3 copies of a string from L, which will have more characters in that string than the one from L squared, and so on. So each of these will give me a string that is longer than any string I had already, which means there's no longest string in L star here, which means that there must be an infinite number of characters in L star. How many understand this? Very good. So now here you've seen your first language with an infinite number of strings. Either the empty language or the language containing the empty string, which is the trivial language. So why is L star going to be finite in those cases? What is L star of the language containing the empty string? Yeah. Yeah, so if we go back here, no matter how many times we concatenated the empty string with itself, we still got the empty string back. So if my language only had the empty string in it, L to the power 0 was equal to L to the power 1, which was equal to L to the power 2, which was equal to L to the power 3, and so on. And all of them only had one character in them. How many understand that? Now where was I? Here. Okay. So, and the computer's frozen. There we go. All right. So now what do you think happens if L is the empty language? Any guesses? What is so if we have empty star, what does that equal? So looking for a guess. Were you trying to raise your hand? So you think that there's one string in that language? Are you saying the empty language or the language containing the empty string? So this is kind of just a convention that we do it this way. It kind of makes sense in certain situations why we do it this way, but it's not like necessarily natural in every case. You could put an argument for both of those cases, either the empty language or the empty string. How many think that it's going to be the empty language? How many think it's going to be the language containing the empty string? Okay, so here's like a mnemonic for how you can remember which one this is. What is 0 to the power 0? 1. Yeah, so what do you think this is going to be then? Right, so this should be the language containing the empty string. So this is that. The reason for that is you can see we have L to the 0 power here. We said 0 to the 0 is 1. So the empty language to the 0 power is the language containing the empty string. That's just the convention we use for this. And it just makes a lot of formulas more convenient, basically, simpler that way. There's fewer special cases when you do that. But the empty string to the power 1, that's still the empty string. The empty language to the power 1, that's still the empty language. The empty language to the power 2, that's still the empty language. Why is that? Why is empty language to the power 2 the empty language? What is empty language to the power 2? Yeah. Yeah, so we said the empty language to the power 2 is the empty language concatenated with the empty language. So now if I find the string on concatenation, we said you take a string from language 1, which in this case was the empty language, and you concatenated it with a string from language 2, which was also the empty language. So how many choices are there for strings from language 1 in this case? Right, there's 0. How many strings were there from language 2? 0. So there were no strings that I could pick here to build this set, so this set has nothing in it. How many understand this? So this follows from this definition right here. So that was a proof. We just did a proof. Good job. All right. So if L was the empty language, then L star is the empty language to the 0 power, which we said was always the set containing the empty string, which we call the trivial language. So that's always the trivial language, union empty, union empty, union empty, and so on. So we've got an infinite number of the empty language all the way over here, union together with this language with one thing in it. So L star has one thing in it. How many understand this? This is something you just kind of have to memorize. All right, so now we also have L to the power plus here. And what is the problem with this? There we go. Okay, so there's two different ways that we use plus just for added confusion in the class. So we can have plus meaning union, where you have like L1 plus L2. So that's a binary operator. Or we have the unary operator plus, so that's L to the exponent plus. And this is everything from L star except for the L0. So it's L1 union L2 union L3 and so on. So L star is 0 or more copies of strings from L. L plus is 1 or more copies of strings from L. And we define this to be equal to L concatenated with L star. So what if instead of A star, I considered A to the power plus? What would I get? Yeah, go ahead. Yeah, everything except for the empty string. So I get A, and so on. How many understand this? Okay. Yeah. Yeah, so let's try it. What if L was the empty language here? So the empty language plus. Okay, well, what's the empty language to the power 1? Right, that's the empty language. What's the empty language to the power 2? Right, so all of these are going to be the empty language. So what is L plus? Right, so in this case, L star actually has more strings in it than L plus when L is the empty language. Ah, yeah. Right, so let's go back to our definition of concatenation now. So if we have, so we're doing language concatenations, we have L1 concatenate L2. So we have the empty language concatenated with the trivial language here. So now we said that the definition of that is you take some string from the first language and some string from the second language, and you concatenate them together, right? So how many options are there for what to put in for what we can take out of the first language? Yeah, so there's nothing in language 1. That's the empty language. So it doesn't matter if there was something. Nothing that we could pull out of L1. So there's no pair of strings that we can grab and concatenate together. Trivial language acts like the multiplicative identity of concatenation, where if you have any language concatenated with a trivial language, you get that first language in return. Set with negative cardinality. Any questions? Any more questions? Okay. Let's see. So, I was hoping to save this for next time. So instead of doing this, we're going to talk about the bird, because I like the bird. Does anybody know how the bird works? What's in the glass, or the cup? Yeah, so the cup just has water in it. So the bird here, it's just sitting there wobbling for a while. I wish I could show it to you on the screen or something to make it bigger. Does anybody know a way I can do that? No? Okay. But there's some sort of fluid in this bird. And you can see that the bird is sitting there waving its head back and forth. And as it's doing that, this red fluid that's inside there just slowly travels up the tube. And then when it travels high enough through the tube, the bird gets top heavy and tips over. And then the fluid drains all the way back down to the bottom, and it repeats over and over and over again. Why is that fluid traveling up the tube? Yeah. Yeah, so the key is that the head, because it's wet, is colder than the butt, right? So there's evaporative cooling going on with the head. So as the head's waving back and forth, there's air that's moving across the head, which causes some of the water to evaporate, which causes the temperature of the head of the bird to decrease. What does that do when the temperature in the head of the bird decreases? It changes the pressure of the vapor that's in the head versus the pressure of the vapor that's in the butt. So since this reduces in pressure, in order to equalize, the fluid has to change up. There has to be a smaller volume of gas up here than there was down there in order to equalize the pressure. So the substance, this red substance in there, does anybody know what that is? This is a very obscure fact. I believe it's called dichloroethylene, something like that. Why do we use that? The key property that we have of this fluid is that it has a very steep vapor pressure curve around room temperature. So for, let's see if I can. So for any fluid that you have, you've got some vapor pressure have to have this fluid travel up, cause the bird to be top heavy, to dip over and exchange the pressures in the top and the bottom. And then it dips its head into the water so that its head stays moist, and it repeats over and over and over. So this is actually a Carnot engine. So this is the heat reservoir down here, and this is the cold reservoir up here. And then the work that's being done is the traveling of the fluid up through the bird to make it top heavy and tip over. And what this says is that if we had a different fluid inside here, we actually wouldn't be doing any less work. We just might get like a different frequency in the oscillation or something like that. So that's what Carnot tells us, is that it didn't matter that there was the dichloroethylene in here. It's just that's the most interesting stuff to put in there. All right, well, I guess I'm going to let you guys out about 5 minutes early then. If any of you, if Professor Robins gave you like permission to enroll for the course and you have a course action form, I can actually sign that for you, so just come on up.